We're going to watch a short commercial from television a few years ago. I want you to think about what's happening in this video.
Mr. Hill, there's something wrong with Scooter.
Don't worry about it. I kept the receipt.
Oops! Someone forgot to boost!
Mr. Hill, there's something wrong with Scooter. You saved Scooter! Yeah!
Minute Maid enhanced with a natural energy boost. Put good in, get good out.
Let's think about what happened in this commercial. Was it completely realistic? No, of course not. But you saw that Mr. Hill rubbed the balloons on his head, and then his hair stood on end, but when he touched the balloons to the rabbit got what? The rabbit got a shock. So, probably balloons aren't going to be able to give a rabbit enough of a shock to restart its heart like a machine in a hospital would do. But if you do rub balloons together, you get something called static electricity. And if you touch them, you might get a teeny tiny little shock. So at least that part of the commercial was realistic. Let's think about what we learned about atoms earlier in the year. Atoms have a nucleus with positive protons and neutral neutrons. The electrons are negative, and the electrons are whizzing around, so they're going in circles orbiting around the nucleus, and because they're on the outside of the atom, sometimes those electrons can move. They can get lost, they can gain more electrons. Electricity is just the energy of electrons moving from one point to another. So if you look at the big yellow circles, imagine those as the nucleus of an atom. So we have several different atoms nuclei here. So here's one nucleus, here's the second, here's another, here's another, here's another. And see the little black dots moving from nucleus to nucleus? Those represent your electrons. So electricity is flowing through this material because the electrons are moving from atom to atom. Remember, electrical energy can be transformed into other forms of energy. We learned this in our last unit. For example, in this light bulb, electricity goes into the light bulb. The light bulb transformed that electrical energy into thermal energy or heat and radiant energy or light. So one form of energy becomes two different forms of energy. Now, atoms normally are neutral, meaning they have the same number of protons and electrons. So if you have 10 protons, you're going to have 10 electrons. Remember when we did this in class? So you could use the periodic table. The number at the top, this 8, is your atomic number. This number at the bottom is your atomic mass. Now to find the number of protons, you use the number at the top. The atomic number is your number of protons. Neutrons you're going to subtract. So I'm going to look at 15.999. That's going to round up to 16. Okay, 16 minus 8, well, that's 8. And then to find the electrons, I told you it's just the same as the protons. So unless you have an ion, normal atoms would have the same number of protons and electrons. Well, sometimes atoms aren't normal anymore. Atoms become charged. That means they gain or lose electrons. When that happens, they become charged, positive or negative. Watch, sodium's going to give that electron to fluorine. Now look what happens. Sodium's going to be positive, fluorine's negative, and we know opposites attract. This makes an ionic bond. So when you lose the electron, you're going to become positive. Look at the cartoon. I lost an electron. Are you sure? I'm positive. Ha ha ha. Corny science joke. But when an atom loses an electron, it still has all of its protons. So now it has more protons than it has electrons. On the whole, it's positive. If you look at the one on the right, it must have gained the electron. These things always happen in pairs. If you lose an electron, someone else gained it. Now the atom that gained the electron, this guy here on the right, is negatively charged because it has an extra electron, and electrons are negative. Just like with magnets, the law of electric charges tells us that like charges or same charges repel each other, but opposites attract, so just like magnets. So imagine these are balloons made out of different materials, and the balloons are hanging by a string. So the two red balloons have negative charges. The negative charges repel. See how they want to be far apart? Same thing would happen with the blue balloons. That's a tongue twister. So the blue balloons are positively charged. So again, you can see those two are going to repel. This one here and that one there, they repel each other. But in the third picture, we have the negative and the positive. They're opposites. And what do opposites do? They attract. So very, very similar to magnets. Now, just like magnets had an electromagnetic force, here we just have an electric force. So the electric force is between the positives and the negative. And it depends a little bit on the size of the charge and the distance between them. So here we have two charged objects. If you look at the rod that she's holding, there's a couple positives in there, but look at all the negatives, the little black dashes. So there's way more negatives in this rod and way more positives on whatever this board or piece of foam or whatever it is. So the negatives and positives attract, but they have to get close. They're not going to attract from across the room, but if you get them close to each other, they will attract. So it depends on the size and the distance between the charges. Now, just like there was a magnetic field around a magnet, there's an electric field around objects too. Now there's two types of electricity. The one we're going to talk about right now is static electricity. The other type is current electricity. Static means stable or stay. So this is electricity that stays in one place and builds up. Doesn't mean it stays there forever, but at least it stays there for a while. Think of students going to science class. So normally when you would come to science class, you would stay there for 90 minutes before you leave. That's kind of like static electricity, where current electricity is constantly moving. So you might think of current electricity as students walking through the hallways. They're not staying in one place. Here's a great example of static electricity. See how his hair stands on end. What's actually happening is each strand of hair is repelling the other strands of hair. Here's a great example of current electricity. See how it doesn't stay in one place? The electrons continuously flow. They're moving from one atom to the next to the next. So static electricity stays in one place, at least temporarily, like kids sitting in class for 90 minutes. Current electricity keeps moving, like people wandering the halls. Here's a great example of static electricity. Remember, static means stationary, stay, not moving. Well, this guy took some clothes out of the laundry and he's got his boxer shorts attached to the back. They're clinging by static electricity. If you've ever taken clothes out of the dryer and they want to stick together, that's what's going on. They've got static electricity. The static built up on the clothes and it stays there, at least temporarily. Now, static electricity does not stay forever. So static electricity will stick around for a while, but eventually it will go away, and we call that a discharge. So the static is the buildup of the charge, and then when it goes away, it's a discharge. We lose the charge. It often produces a spark. So if you've ever touched a doorknob or something metal and gotten a little zap, that was actually a discharge. And what it really is a miniature lightning bolt. Lightning is very similar, it's just larger. So it's also static electricity. So sometimes you get a buildup of charges. So up in the sky, let's say we've got all these extra electrons. Those are negative. So we have a buildup of negative charges. And the ground lost those electrons, so the ground is now positive. Well, what do we know about opposites, negatives and positives? They want to attract. So what's going to happen? Discharge. So all of those negatives that were up here, they come traveling down through the lightning bolt to the ground, and now everything's back to neutral. No more static electricity. But then the process can start again. So maybe now we start building up electrons in the sky, and the ground becomes more and more positive until we are back to another discharge. charge. All right, you've got some questions that you need to answer, and then you're going to continue.